Hi everyone, it's me, Carolyn, and we are beginning chapter 12, and we'll be looking at our goodness of fit test, which is a test that looks to see if data in certain categories follows a certain distribution, whether that distribution be very complicated or rather simple. I am going to turn our screen over to our guided notes so that we can get started. Again, let me wait till it clears switches here. There we go. Zoom out a little bit. It looks a little big here. Okay, there we go. And this is chapter 12 of our textbook that we are using, and not find my pen. I'll just have to grab another one. All right. Oh, sorry about that. But this is our 12.1, which is our goodness of fit test. And it is basically wants to determine whether a frequency distribution. So if you have different categories, if it follows a specific distribution. And when we get into the examples, it will help that make sense. So, whoops, I can't find a middle here. All right, so the hypothesis test that we're going to be doing, like all of the hypothesis tests we've seen, have 5 steps to them. Now, this one will have some similarities in the fact that it does have the same 5 steps, but those steps will be slightly different because this is, of course, a different test. So first of all, our step 1 is to write those hypotheses. And we have is our null hypothesis to assume that it does follow that certain distribution, whether it be stated distribution or some assumed distribution that they believe is to be true. Versus the alternative that the random variable does not follow that distribution. Step 2, as it has always been in the past chapters, is to find that alpha level or to set that alpha level, depending on how cautious we want to be. We do have some requirements for this to work, is we want to make sure that all of our expected counts, and we'll talk about what that is in our example so you can get a clearer understanding, that all of those expected counts are greater than or equal to 1. We don't want to have a category that has nothing in it. So we also want to make sure that no more than 20% of our expected counts are less than 5. So we don't want to have categories that are relatively small. So we want to make sure our categories kind of have stuff to work with. Another thing we will have to do is calculate all those expected counts for each of those categories. And again, when we get into those examples, we will see some of those things happen. Our test statistic, you will notice, is a chi-squared, which is equal to the sum of, and we have this OI minus EI, and we have to subtract those and square them and divide by the EI. This OI is going to be your observed count for each of those categories. EI is the expected count, or how many we expect to have in each of those categories. And then we will subtract and square them and then divide. I will go through some of this. I will show you how we would calculate the expected count at each piece. I won't do them I won't do them in the second example, but I will do them for the first example. I will start this test statistic for our first example. The nice thing is these are kind of tedious to work through. They're a lot of work, a lot of grunt work. And with technology, we now can take all that extra calculations out of the picture for us, and we can get those results rather quickly. Notice also this is a new curve. We do not have a T or a Z. We have something called a chi-squared. So it is kind of like a funny looking X. It is a Greek letter. It is pronounced a chi, so the K with the long I sound, and it is a squared, so chi-squared. So we will be looking at a new curve. Step 4 is to find those critical values, which will correspond to the alpha level. or of course to find that p-value which corresponds to the test value. Again, similar, but since we're dealing with a new curve, we will be looking at a new table. This is always a right tail test, and we'll see that in just a minute looking at the pictures, what that's going to kind of look like. So before we go to that step 5, which we all know what that is, we're going to look a little bit more at that curve. So first of all, the chi-squared is not a single curve. It is a family of curves similar to our t-distribution was also a family of curves that were based on some kind of degrees of freedom. The degrees of freedom here in this situation is calculated by taking k minus 1, where k is the number of categories. And when I walk through those examples in a moment, we will see the k, and we'll talk about that k minus 1, the degrees of freedom. A little bit more about this curve. It is not symmetric. Unlike the t curve, which was nice and symmetric around 0, and the normal curve, which was symmetric around 0, it is also not centered around 0, but it is completely positive. One thing we will see is that as the degrees of freedom increase, it starts to look a little bit more normal, but again, not centered at 0. So it does start to look like a symmetric curve. So let's kind of look at some of those pictures so you can kind of see. And I did put 2 pictures in here. Here you'll notice that k is 1 and so forth. So if we only have one category, it's kind of hard to talk about a distribution if everybody's lumped into one group. So that's why it doesn't even really look very nice. It's just this yellow curve, which you can't really see in this video, but if you printed out the guided notes from our course site, there it is. You can see that curve here. Also, if you go on to your internet, you can pull these curves up yourself. That's kind of where I got them. And here's a green one for 2. And once we get to 3, you can kind of see this curve feeling a little bit more normal. And as n increases, or the number of categories increases, not n, but k increases, it starts to get a little bit more normal looking. You can see this a little bit more closely if we zoom out. Notice we only went to 8 here. Notice where 0 is. It is not in the center of our curve anymore. It is off to the left-hand side. So these are not negative whatsoever. It is completely positive because we're adding a bunch of positive numbers together. And as k increases, the number of categories increases, we do see that symmetry showing up. We also see it kind of looking normal. But again, not normal because it's not centered at 0. Step 5 is, of course, to make our decision, either to reject or not reject. I want to remind you, we do not accept the null. We just kind of like when we don't say that a person is innocent, we always say that they are not guilty. So we will not reject. And then, of course, we write the conclusion, which goes back to the original problem and puts it more in layman's terms. So if you were to publish something, you could say that we have found enough evidence to show whatever it was that we were trying to do. Or there was enough evidence, there wasn't enough evidence. But we go back to that original question. You would not publish in a journal of some sort that said, oh, we rejected the null, because most people would not understand that language. All right, so let's look at some examples. And I do have 2 of them. And I am going to use StatCrunch again to help reaffirm everything, but I'm also in this one going to look at some of the things, how we calculate some of the pieces. So the first example I have is about peanut M&Ms. And if you go out to M&M's website, they do have these numbers out there. I do not know if these numbers are still valid, because I have not been to that site in a while, but I'm going to go with, let's just say that according to the manufacturer of M&Ms, the bag is supposed to have 12% of the peanut M&Ms are supposed to be brown, 15% are supposed to be yellow, 12% are supposed to be red, 23 blue, 23 orange, and 15% green. A student wants to kind of find out, is that really the case? So he checks it. What he does to check it is he pulls out a very large bag and he counts how many of each color he has, and he finds the following. That in his bag or couple of bags or his group, he had 53 brown, 66 yellow, 38 red, 96 blue, 88 orange, and 59 green. These numbers here are what we would call the observed values, because that is what we observed in our group. Okay, and what we're going to try to do is test if this bag follows that manufacturer, and we're going to use alpha 0.05. Again, if we were doing this as a statistician, we would choose our alpha level based on how cautious we would want to be. Do we want to be 99% accurate, 95%, and so forth? So again, a lot of times it depends on the word I'm looking for, the importance of the test, whether or not the colors in the bag are actually following the manufacturer. I guess it would depend on if you were allergic to one of these and you wanted to make sure that you didn't get so many. Anyway, that's enough of that. But we're going to go through our 5 steps. So step number 1 is to write our hypotheses. So again, the null hypothesis and our alternative hypothesis. The null hypothesis will always be in these types of situations that the peanut M&Ms follow the manufacturer's distribution. In other words, we get that 12% brown, 15 yellow, etc., etc. Okay, so the null hypothesis is that it does fit the stated distribution. It's a stated spread, or however we're distributing these pieces. The alternative is peanut M&Ms or peanut M&Ms. I don't know if I needed the word "the" in there. Do not follow the manufacturer's distribution. Now, we could get a little bit more detailed in our hypotheses by putting those actual values in here if you had wanted to. I am not going to because they're just right above us. So again, this is just educational purposes. We are not publishing this, but if I didn't have the original and I were publishing and I wanted to show all my 5 steps without having the problem here, I would have then put that information in there because everyone would have wanted to know, well, what in the world is the manufacturer's distribution? Step 2 is to find that alpha level, and our alpha level is going to be 0.05. Okay. Step 3 is to do that test statistic. Okay, so I'm going to pull this off to the side here, pull my sheet back again. We have to do all of this stuff. So I have my observed, those are here, those were the ones in the problem, that counts that the student got when he counted his M&Ms, but we do need all these expected. Okay, what would we expect if this was true, if they followed that distribution? How many brown would we expect to see? How many yellow? How many red? So the first thing I need to do is find out how many M&Ms we're dealing with. So I'm going to add up all of these values. So I'm going to add the 53 plus my 66 plus my 38 plus my 96 plus the 88 plus the 59. And I have that we have 400 total M&Ms. Okay, and we expect 12% of those to be brown. So to find 12% of the 400, that word "of" kind of tells me to multiply. So I'm going to take 12% times the 400, and I get 48. So I'm going to put my expected kind of above here. So these were the observed, and I'm going to put my expected. So I expect 48 brown. Yellow, we had 15%, so 15 times the 400. That gives me 60. Red, we expected 12%, which we already did, so 48 red ones. Blue is 23%, which is 92. Orange is the same, and green is at 60 again. Okay, so those are all my expected. So now if I were going to be calculating my test statistic, I have to take my observed value. So here's my formula. So that was my 53. We need to subtract off the 48. We need to square that and then divide that squared number by the 48. We will do this again for the next one. Notice I'm going to be adding all of these together. I'm not going to do all of this, but we do each piece. So we would do that all the way down the line. Now, just to make sure if you were doing this by hand, luckily for us, we have technology. I would have to do that 53 minus the 48 first, then square that number, which gives me 25, and divide that by the 48. Okay, so make sure you do your correct order of operations each step of the way. Okay, but again, I'm going to go to StatCrunch to actually calculate this all the way out for me. Save myself a little bit of calculator work. Okay, also while I'm in StatCrunch, I'm going to be getting step 4, which is, I can't actually get the critical values, but I can get my p-value. So my critical values are found by looking at our chi-squared table. And my chi-squared table. Okay, because this is a chi-squared, we're using a different table. And we can get our critical values, which kind of set up the boundaries for our critical region or that rejection region. Okay, so we have 1, 2, 3, 4, 5, 6 different categories. So our degrees of freedom is at 6 minus 1 or 5. So we had 6 categories, the 6 colors. So our degrees of freedom is 5. Also, we're always doing a right tail test. So this gives me the area in the right. So that means I'm going to be looking for that 0.05. And here is that 11.070. So my critical value is that 11.070. Okay, I'm going to go to StatCrunch to finish off getting my test value and to get my p-value, just so that we can see how this all works. So give me a moment here. We'll switch screens and we'll go to our StatCrunch. Oops, that's not StatCrunch. Oh man, I don't see StatCrunch. Don't think that's it. There it is. Okay, hopefully you guys can see StatCrunch here. Yeah, okay. So StatCrunch, what I've done ahead of time is I did create some columns here. I created the color. I put in our observed values here. I also put in the percentages. If you have your percentages, you can put those in here, or you could put in the expected number. StatCrunch can work with either, just so you are aware of that. It will not matter which one you use. It can recognize the difference. So basically, I think it adds up these numbers. If you get 100, it's going to assume that you are doing percentages. So to do our goodness of fit, it is going to be under our stat button, which is where the tests that we've done to this point are located. You'll notice if you go down here, we do have a goodness of fit because we are trying to fit a distribution amongst our categories. It is a chi-squared or chi-square. The observed values that I have here are in my observed column. So I will click that. My expected are in, and I'm going to choose the expected color so that I'm choosing the 12, 15, 12, and so forth. Okay. There's nothing else that we need to do here. And we are going to compute. I'm going to, whoops. And the reason we don't have to do anything more is because if you remember, trying to get this to slide over for us. Here we go. Our p-value is associated with the test statistic. So we don't need to have an alpha level in order to do the test statistic and the p-value. The alpha level will be used later. The alpha level we did use to calculate our critical values. So this does it without any alpha level. So it doesn't matter. So you can choose your alpha later if you want to. But here's our observed values. You'll notice that I had chosen the 12, 15, 12, 23. Those numbers are not there anymore. They actually calculated those expected values for us. So we didn't actually have to do that. Another nice thing about these programs is it does most of the grunt work for us. So I'm going to write my test statistic, which is found up here in that chi-squared. That's the 3.56. 3.568, that's enough digits. And my p-value, we have 0.613. Okay, notice there's my 400. This is a nice check to make sure that did I type in my numbers correctly? My degrees of freedom was 5. So if you didn't have your degrees of freedom, it does show you that as well. So I am going to go back to my guided notes and finish this problem off. And we'll let it catch up. That's refreshing. So there is my critical value, my test value. There's those critical values, and there's my p-value that we got from the StatCrunch. So here we got our test statistic and our p-value. So for step 5, we have to decide, do we reject H naught or do we not? And if we were doing our critical value, what it does, chi-squared, remember, is kind of at 0. So here is 0. It is always positive, like every other curve that is a probability curve. This 11.070, and how you shape the curve really doesn't matter. But this sets up kind of like our rejection region, that critical region. And then we would put that 3.568 into here. So 3.568, I don't know exactly where it would be, but it's in this area. It's on this side of that critical value. It's not in this little tail. The other method for making our decision is we looked at our p-value and we wanted to say to ourselves, is it smaller than the alpha level, which we had as 0.5? That is a no, it is not. No, it is not in the rejection region or critical region. So our step 5 is we will do not reject H naught. In other words, we are finding it not guilty, not saying that they're innocent, we're saying it's not guilty, which means that there is not enough evidence to show that peanut M&Ms do not follow the manufacturer's distribution. And I'll put in the word percentages. Okay. You could, again, be a little bit more detailed and put those actual numbers in here, like the 11, the 12%, and the 23%, and all of that piece as well, just if you wanted to be more detailed. I will notice on this problem, I'm going to go back to the original numbers. We did not have exactly what we were expecting. So we saw 53 brown in our bag, but we should have only gotten 48. None of these numbers match up. But the reason that we didn't reject is they weren't different enough to say that we're too close to the expected. We're not far enough away from the expected to say that they aren't following that distribution. All right, let's do another one. So I have another one down here, because not all distributions are given to us in percentages. Sometimes they are, sometimes they're not. And this one is saying that a researcher wants to determine if bicycle deaths are uniformly distributed over the days of the week. So in other words, uniformly, you have to remember what that means. And that means evenly across the board. Okay. If I'm just glancing at these numbers, because she randomly selected 200 bicycle deaths recorded which day they happen, these numbers don't look like they're about the same. But are they different enough to say that the bicycle deaths are not uniformly distributed? And that's why we do these tests. And maybe we're trying to determine if something else is uniformly dispersed amongst different age categories or different genders or different races. These are the kind of tests that we would use to do something like that. So again, we're going to do one of our tests. And we're going to write out our hypothesis that bicycle deaths uniformly, like the word uniformly, evenly distributed over the days of the week. Versus the alternative, bicycle deaths are not uniformly distributed over the days of the week. So that's step one. Step two is to find our alpha level. Here's my 0.01. I just pulled that from the test. Step three is our test statistics, which I will let StatCrunch do for me. Step three is that chi-squared. Step four is to either get our critical value or our p-value. And again, I like to do both just so we're exposed to both of them. But in reality, you only need to do one. As technology becomes more and more used, critical values are tending to fall by the wayside. P-values are becoming more popular. A lot of times in statistical reading, you will hear or read what the p-value was. That is this p-value that they come up with. So sometimes they don't tell you what the test statistic is because the normal person doesn't care, doesn't understand it. If they have some understanding of statistics, p-value might be one of those things that they remember. But we're going to get that critical value just for practice. So we need that degrees of freedom. So we have 7 days of the week. So that's the number of categories we have, -1. So we have 6 degrees of freedom. 6 degrees of freedom, and our alpha level is 0.01, which is way down at the end here. There's our 0.01. We're going to 6. So 16.812. I'll write that in here, 16.81. And now I'm going to go to StatCrunch to get my test value, my test statistic, and my p-value. So switching gears again. Let me share. Okay, get rid of this one because we don't need that anymore. Here is the information. I did type this in earlier, just again to save time in these videos. Always make sure you double check, your data when you're typing things in. A lot of times that is the number one reason things don't work. But again, we are going into our stats and we are doing a goodness of fit. It is a chi-square. We are going to be looking at the observed day, because that is kind of what I called my column. Notice here the expected, we can either have some percentages or we can do this all equal. Now remembering uniform does mean all equal. So we're going to see that. So I'm going to hit compute. Here come my results. Very quick, a lot faster than you could ever do it by hand. We did have 200. That's kind of a double check on the number of deaths that we looked at. So there's my number of deaths to 200. Degrees of freedom, there's that 6 that we had calculated earlier. Here were the observed. Notice all of those expected values are equal to each other. So there is our test statistic, that 19.03, and our p-value of 0.0041. All right, back to our guided notes to finish this problem up. Let it refresh. Takes a little while. So there is our test statistic. Here's our p-value. Here was our critical value. I'm going to draw my picture so you can kind of see the picture. I like drawing the picture still too, even if you do use a p-value, because it kind of helps illustrate what's going on. So here's our critical value. There's that 16.812. That is remembering setting up this area. The area here is at 0.01. So those two pieces go hand in hand. The critical value with that tail. To test, we want to locate where this 1903 is. 1903 is bigger, so it's going to be up here somewhere. So 1903. And if I had another color and shaded this P, the pink region, that's your p-value. That's the 0.0041. The area that goes with that test value. So notice here that our test value was in the critical region. Yes, it's in the critical region, or the rejection region. Critical, rejection. Oops, I spelled that wrong. Or we can look at our p-value. It's smaller than the 0.01 or the alpha. Is there alpha? Yes, it is smaller. That is true. So we will reject. Okay. Which means what? Well, if you're telling the normal person, that means nothing to them. What they want to know is that there is enough evidence to show that bicycle deaths are not uniformly distributed among the days of the week. Okay. And then you might want to start doing even more research, and you might be looking and saying, okay, so which one has the most? And then you might be saying, well, Friday has more than Sunday. But then you would have to do one versus another. And that goes back to chapters 9 and 10, mostly 10. If you wanted to compare, actually chapter 11, where we compare 2 different days. So that would be doing some of that work, breaking it down. So here we just get an overall view, but we can break it down going back to some of the other things that we have learned earlier. I am going to stop sharing. And I will tell you that this does conclude the goodness of fit. Again, remembering goodness of fit, we're trying to see, does our categorical data, those numbers in each of those groups, follow some sort of distribution, whether that distribution be stated as percentages or uniformly, or maybe even something more complicated. I mean, just because I've done the two examples, you can have something a lot more complicated, maybe something follows an exponential shape. But that would be something a little bit more complicated than we're going to get to in this class. Again, this class just touches on things. But I'm going to stop here and tell you to have a fabulous day and that I will see you in the next video. Hello?